Okay, so there are people getting coffee, but they're gonna come in the next 30 seconds. So for the 30 seconds, I might just do the introduction. So our next speaker, Weilin Li, from right now the Courant Institute of Mathematical Science in New York. And he will be talking about, so there's relations, I guess, with the previous talks on minimum weighted norm interpolations and Fourier scattering transform. And the floor is yours.
Okay, all right. So thank you for the introduction, Simon. It's a pleasure being here. So I'm here mainly filling in for Wojtek. So I've decided to talk about kind of two topics that are related to some of the other talks given so far. And at the end of this talk, I'll connect the two. Okay. So a figure like this, you've already seen before. So let me just talk about it briefly. So this figure comes from this paper by Belkin et al. In PNAS in 2019. So the content of this paper is that they were looking at this this is called empirical risk minimization. The idea is that given some data points xj's, yj's are their labels, I try to fit a function belonging to this hypothesis space script h that minimizes this L2 error. And this is just like the common technique in statistical learning. And there's classical theory, the bias variance trade-off, which basically says that I don't really want to overfit my data. Like if I take a very big hypothesis class H, I can fit the data perfectly, but when it comes to predicting new examples, I might do a terrible job. And in this paper by Belkin et al. In 2019, they proposed this this double descent curve here, where they argue that actually in many modern machine learning algorithms, data science algorithms, one can actually take kind of how big H is, H to be a very huge function class. One can still get perfect training error, but still do well when it comes to test time. They call this double descent because of these two curves here, the first descent here, and then the second descent here in the over-parameterized regime. So this way of looking at things is quite different from, say, classical learning theory or statistics or approximation theory. In those classical theories, typically one fixes the function space and looks at the number of samples going to infinity. And one, of course, hopes that the error would go to 0 in that case. But here, the number of samples is fixed. N here is fixed. And what we're doing is changing the hypothesis class. In other words, you are allowing yourself more and more complicated algorithms for fitting the data. OK, so that's kind of like the starting point of this work on minimum norm interpolation. I mean, everybody here knows about frames. So the idea of approximation using over-parameterized or redundant systems is certainly not new or foreign to anybody here. So I started thinking about this from just basic principles. So let's look at, say, trigonometric interpolation. Let's say there's n data points on the, say, the torus across R. And what I'd like to do is I'd like to fit these data points with trigonometric polynomials up to degree capital N. So here I have this function space of dimension capital N. And if, 2n plus 1. And if 2n plus 1 is strictly less than the number of samples, I can't fit the data perfectly. The best I can do is this L2 error. But on the other hand, if there's more parameters than number of samples, then I can fit the data points perfectly. So there's some non-uniqueness here. And well, what I'd like to investigate is what happens if I try to find an interpolant of the data points with smallest, say, Sobolev norm. Okay. And so, okay, let's see what happens on just an example function. Let's look at this Runge function here. It's been normalized to be between 0 and 1. And let's say I sample this particular function at 35 data points randomly. And I calculate these trigonometric interpolants for various Sobolev parameters. We measure the error in the L infinity norm and just average over 100 trials. And this is the figure that we get here. So as you can see, with 35 points, whenever the number of parameters is less than 35, I just do the best L2 fit of the data, and we have this classical U-shaped curve predicted by the bias variance trade-off. But in the overparameterized regime, depending on which Sobolev parameter we pick, we get different errors. And something interesting happens, which is that for certain parameters, Sobolev smoothness parameters, the overparameterized interpolants actually do better than the optimal underparameterized ones. So this figure is just saying that, maybe taking more parameters than necessary isn't a terrible idea. Just to give you some intuition as to why this works, or why it doesn't work. If we look at just the minimum L2 norm interpolant of the data points, so here I have this Runge function, and the green points are its samples. The red curve would be the minimum L2 norm interpolant with 73 parameters. So it's like a trigonometric polynomial of degree up to 36. So the minimum L2 norm interpolant would oscillate wildly because, well, we're trying to interpolate the data points with a function with smallest L2 norm, and so oscillate wildly, yielding a poor approximation. But something like the minimum W1 norm interpolant, which will be almost like a piecewise linear one, will do a much better job at approximating the function. Okay. So the question is, can we try to understand this in a more general context beyond just, say, trigonometric interpolation? And the answer is yes. So we'll phrase this in a more abstract way, but it still captures the same flavor of the example given earlier. So let's say we fix a sequence of L2 orthonormal functions, these phis. Now, the orthogonality is not very important. For the purposes of this talk, it allows us to say a couple of other things that are in the paper, but not relevant here. But what's important, and this will come up later on in this talk, is the normalization. So it's important to remember that these guys have been normalized to have unit L2 norm. So again, just like the trigonometric case, they generate these hypothesis spaces. And one can define this type of weighted norm. So just like with the Sobolev norm, one looks at the basis, or kind of these coefficients of f in the phi basis. And then the omega norm, or this weighted norm of f, will just be the sum of kind of like these Fourier coefficients of f weighted by the omegas. And so given lowercase n data points, where the x's are in the domain and y's are reals, they could be taken to be complex, but we'll just look at the real case. Whenever capital N is sufficiently large, we'll look at these minimum omega weighted norm interpolants of the data. And what can we say about these things? Okay, I want to keep this talk kind of at a high level, so maybe I don't want to go through these details too carefully, but there exists some abstract conditions that will make everything go through. But they're quite general. So, for the first one, we just need a metric measure space. For the second one, the existence of the interpolants are necessary to even pose this problem correctly. And then the third is some compatibility assumption, which relates the omega with the phis. And so the main result here is that under these abstract conditions, which will be satisfied for a variety of learning tasks, for any data, there exists a f infinity such that these interpolants with capital N parameters converges to f infinity in LP of mu for every p between 1 and infinity, including the endpoints. And this f infinity is a very special function. It's the interpolant belonging to the reproducing kernel Hilbert space of this kernel capital K, where this capital K is this kernel here that's defined in terms of the phis and the omega. Okay. And so this rigorously establishes what some people refer to as like the implicit bias of this algorithm. So it's saying that as we increase the number of parameters, the algorithm is not searching through a space in a very uncontrolled, chaotic way. It's doing something quite well behaved, and it'll tend to some limiting function here. So as a corollary of this, if the labels y are generated by sampling some f star, then one can get a bound on this generalization error, the error between f star and the degree or the n parameter interpolance in LP. And this error will have to converge to this limiting error here. But as we saw from Simone's talk, we shouldn't expect this guy to always be small, because remember, lowercase n is fixed. So there's always some error. You always have to make some error. But it could be very small, could be very large, which is kind of bad. So if the limiting error is large, then overparameterization for this algorithm will never help. But overparameterization could be helpful if this limiting error is small. Okay. So this problem basically now reduces down to this limiting error, which has already been studied quite extensively in the kernel literature. So it's known that if we sample an f star, provided this f star belongs to the reproducing kernel Hilbert space associated with the kernel K, then sampling, then interpolating using kernel interpolation, this function will approximate the f star in a suitable sense. So as the number of samples increases, so that the kind of the mesh norm of the sampling set goes to 0, then so will the error. Okay. So this is just saying that kernel interpolation is consistent. So if we allow lowercase n to go to infinity, then this is not necessarily a bad idea here. Okay. Just as a quick comment, which is in the paper, but not in this talk, this limiting error can be better understood in very special cases, such as Fourier series and spherical harmonics. The spherical harmonics case has been important more recently because of things like the neural tangent kernel. And in particular, you can reduce the regularity assumptions on f star. So the general theory requires f stars in this reproducing kernel Hilbert space, but one can weaken this, and this is called breaking this kernel barrier here. Okay. So that's it for minimum weighted norm interpolation. I want to switch gears a little bit and talk about Fourier scattering. And this is joint work with Wojtek as well as Ilya Kavalerov, who is also a graduate student at Maryland at the time. So this is something I spoke about several times. In fact, I talked about this in 2018 at Vanderbilt for the Constructive Computational Harmonic Analysis Conference. So the short time Fourier transform, as we all know, is just convolutions of a particular function with these guys, g sub m. G sub m is a modulation of a fixed function g, and these are called, say, Gabor atoms. And they're quite useful for signal processing. For example, if f is an audio signal, then if I were to collect all of these guys and take their modulus, and think of this as now an image, then this is called the spectrogram of f. Okay. But as we know from Mala's work, and Bernard also kind of talked about this as well, we can create more powerful representations of these functions by iterating these high and low pass filters. So here, g, which we think of as like a nice bump function, this is doing like a spatial smoothing. So this is like the low pass of f. And then convolutions of f with these g sub m's are kind of bandpass filters. They capture the higher frequencies of f. We take their modulus, convolve with g, which gives us the low pass. And then for the remaining high pass, we continue this cascade of high pass convolutions with modulus, with low pass, and so forth. And you can build this very complicated nonlinear representation of F. And we call this Fourier scattering, in contrast to Malot's work where he would use wavelets, whereas here we do kind of Gabor functions. So in terms of a network, you can think of this as a predefined neural network with activation, with the modulus as the activation. We take subsequent layers and convolutions here. Okay. Again, I just want to go over this at a high level. So this idea generalizes to other systems beyond just traditional Gabor. So traditional Gabor would be something along this line of reasoning. We have a fixed function g. When we modulate, we do translations in Fourier. So we're like tiling the Fourier domain with these rectangles. But one can look at more complicated tilings like these pineapple tilings. And we define this class of frames called uniform covering frames, which capture kind of the philosophy behind time frequency analysis. So like time frequency analysis is saying we should split up the Fourier domain into pieces of approximately equal size. And that's precisely what we're doing here. Okay. Okay, so in some ways, this is all kind of like old stuff. This is kind of like an old story, but I promise I'll tell you some new things that I did not talk about in 2018. So we mainly applied Fourier scattering to data sets called hyperspectral images. These are three-dimensional images, usually generated overhead by maybe a satellite or a small aircraft. These are basically images of the surface at various wavelengths. They range from the visible spectrum to the infrared. And the sampling in the spectral domain is quite dense. This is an important imaging modality because by looking at the spectrum associated with one pixel, based off of the shape of these curves, you can try to predict kind of the composition of the material at that spatial location. Okay. So how do we do this with Fourier scattering? The idea is quite simple, I would say. So again, lowercase n is the number of training points, and capital C is the number of classes. So we just want to do some classification on the data points. So you think of each xj as a spectra, and then I want to know what is the material located at that location. So what is the material generating said spectra? And the idea is, well, we'll just transform all of the training points with a Fourier scattering transform. It's going to create some very complicated representation of the data. And we'll use a two-layer one. It'll be clear in a second why we use two layers, but Bernard also talked about this, which was this norm decay property. So because the energy decays quickly enough, there's no point in retaining more and more coefficients. One should just stop at a certain point. And then two layers is usually enough. So, okay, from these data points, we just compute a support vector machine that classifies them. Now, it's not a binary classification. One has to compute a family of 1 versus 1 max margin support vector machines. But this is pretty standard. So these W's are the orientations of the plane, and B will be the offset. So I tried to find an orientation of this plane and an offset B that will try to split my data as best as possible. The second term is kind of how well I do on the training. So am I able to split the training data? And this first term is a regularizer. It's saying that I don't want to make W too big, okay? The reason I don't want W too big is because I want the data points to be far away from the hyperplane splitting. And so a new X is predicted just through this hyperplane. I look at, okay, which side of this hyperplane does it fit on after I perform this Fourier scattering transform. Okay, so these are results on Indian pines. This is a very standard data set, 16 classes, mainly farmland. There's the ground truth, and this is the image that we got through Fourier scattering transform. So in terms of the error, we're making approximately 3%. And there's this other group who used Malot's wavelet scattering transform. Their error was about 6%. So you could say it's a 3% increase, but you could also say it's a 50% reduction in the error. So we found similar results on other standard hyperspectral image databases as well. And these are pretty close to state of the art. Now, I don't really want to compare Fourier versus wavelet. I'll just say briefly why I believe Fourier tends to do better. It's because on hyperspectral images, the smallest spatial scale in each of these data sets is still quite large. So there's really no gain in mixing pixels that are far away, which was what wavelets would do. And the second reason is because the spectra is so oversampled and it's so dense, it's quite smooth, the spectra. So you don't have these jump discontinuities, which would be better handled by something like wavelets. Okay, so again, this isn't really a competition. That's not what I'm trying to get into here. But what I'd like to talk about is this, this final part. And for anybody who does scattering, there's this kind of elephant in the room, which is why does it even work? Okay. And so far, the scattering theory pertains to what, let's say, low dimensional analysis. So given a function f on Rm, M here we should think of as like a small number, 1, 2, or 3, like 1 for audio, 2 for images, 3 for hyperspectra, etc. Generally, the scattering theory will talk about bounding the difference between features of f and s in some norm in terms of their initial difference or some other quantities, okay? And as Bernard mentioned, this is a completely data agnostic transform. And here, any theory for this problem cannot tell you anything about performance guarantees on classification. In this part of the problem, there's no mention of training. There's no mention of anything, any labels or anything like that. So what the heck is actually going on? Well, it's because to actually give performance guarantees, we have to talk about this high dimensional problem. So here we think of X in RD as really samples of this function F. So if M is like, say, 1, so F is like an audio signal, we think of lowercase x as d samples of this function. So little lowercase d here is definitely not a negligible number. It should be quite large. And numerically, what the scattering transform does is it takes this vector and it maps to this new space of dimension capital N, where capital N is going to actually be much bigger than lowercase d. So given n samples of an unknown function, there's an obvious typo here, sorry. This is supposed to be RD. So F star you can think of as the classification function. What we'd really like to do is approximate F star via some composition. So the composition we're doing is first scattering and then some classifier C, where script C depends on whatever training data we're given. And this is a kind of more difficult problem. And it's not as easy to understand because, well, we have to work with functions in a higher dimensional space. We have to take into account training, take into account the labels. So how can we do this? So pictorially, basically, the scattering pipeline is we have a function, we sample it, we compute the scattering features, then we classify. And so far as I know, whether it's wavelets or Fourier or graph scattering, all the theory only pertains up to this final step here. There's almost no theory or no theory that I've seen that will say anything about this final step of the pipeline. So how can we understand this? Okay, well, this is a delicate question because we actually violate pretty much all core principles of statistical learning theory. Because if we think about what scattering does, we map a vector in d dimensions to another vector of n components through this complicated process. But without any downsampling, this capital N is on the order of d cubed because To represent x, which is a vector of length d, I will need approximately d of these g sub m's. Then I have d g sub m's, d g sub n's, so it's d squared. So it's massively over-parameterized unless the number of samples exceeds d cubed, which is unrealistic. The second kind of core principle of statistical learning that we violate is when we do this optimization procedure, we found empirically that small lambda tends to perform best. And why is that surprising? It's because lambda is quantifying the trade-off between the norm of W, which is kind of like lambda is like a regularization parameter, versus how well I fit the training data. So if lambda is very small, then it's telling me I should actually just focus on fitting the training perfectly. I don't need any regularization. And that's, again, very surprising. We should expect poor generalization if this is what we do. Okay, so here is where I think that these energy estimates really come into play. So the Fourier scattering transform satisfies what we call this exponential decay of energy. So at each layer, there's more and more coefficients. But if we add the total energy in the nth layer, then it's bounded above by some lowercase c to the power L minus 1 times the initial norm of F. Okay, so each layer, there's more and more coefficients, but somehow the total energy in each layer is decaying exponentially. Okay. And just to briefly describe the history of these types of estimates, Irene Waltzberger has a result like this for complex analytic wavelets for the wavelet scattering transform in 2017. This is our result that we derived around 2017, 2018. I also presented this at Vanderbilt in 2018 then. Bolsky, Wiatowski also have a paper on these energy estimates, and then Domian, Gilad Lerman, they have a result of this type of flavor for graph scattering. Okay. And the second energy estimate is this energy concentration along frequency decreasing paths. So it says that if I look at n, which roughly represents the kind of the Fourier support of each of these filters, if n is much bigger than m, then one expects terms like this to be quite small. Okay, and the reason I'm bringing this up partially is because to talk about parameters and increasing the number of parameters, we have to fix an ordering, okay? But these energy estimates provide us with like a natural semi-partial ordering of these coefficients, okay? And so let me show you what happens. So on indium pines with 10% of the data, if I pick lambda to be 10, it's saying that I should not overfit the training data. And you can see what happens in this red curve here. The training error is like around 5% and the test error is around 10%. But if I reduce lambda, I reduce the amount of regularization. Hey, look, the training error actually goes to 0 after a certain point and the test error hovers around like 4%. These two vertical lines, so the first vertical line is if I were to only take the 0th order scattering. This first dashed line tells me that I'm only taking coefficients up to order 1, and then all of these are for second order coefficients. So I'm increasing the number of parameters. It's natural that the training error decreases, but somehow the test error is also decreasing. But also surprising is that if we were to lower the lambda parameter even more, then it's saying that, oh, I should not worry about the norm of W. I should only care about fitting the training data. You see that the training error is 0 like very quickly using just a few scattering coefficients, but the test error actually is smaller. So here the test error, if I were to take all coefficients up to order 2, it's about 3%, maybe a little over 3. And then if I were to decrease lambda even more, I fit the training data even faster, but I still generalize well. The training error is even around 3%. So this is quite surprising. Okay, so why does this happen? I think I'm basically out of time, but it's basically this connection to weighted norm minimization, in my opinion. So one can show from the energy estimates, which are for the low dimensional problem, what they translate to in high dimensions is one should think of these data points as in some kind of ellipsoid. And when one is doing this SVM without any regularization, it's almost like doing a weighted norm minimization on normalized scattering coefficients. Okay, so sorry I ran out of time, but if you're interested, I can show you the slides. So thank you so much.
Thank you, Weilin. Are there any questions? From the audience?
I think that's a very intriguing result. Also, where you compare with the different frequency content. Have you used this with like some standard, let's say, shearlet decomposition?
Oh, okay. So I have not done like, say, shearlet scattering. Yeah, that's not really my.
That's fine. Then
Yeah.
let me follow up because I would like to. I mean, I would find it interesting if anybody can somehow explain the role of sparsity in learning, or in whatever context, like the scattering transform.
Okay.
It's really weird. So I don't understand it. But if anybody has an idea whether it helps or does not help classification, say, or these types of problems, right? I think that would be very interesting. At this moment, I don't understand the role of sparsity.
Yeah.
It should help, but it doesn't seem to. Do you have any comment, at least, on that?
Okay. I would say if we're talking about sparsity in a more general sense, about like decay of coefficients, not necessarily just number of non-zero, then the way I'm seeing it is through this connection to weighted norm minimization, is because numerically this scattering of X, okay, you have a bunch of entries, but the entries are decaying exponentially. So if all the X's have norm approximately 1, then these guys you should think of as being on an ellipsoid. And so that's where I think the decay of energy estimates come into controlling the generalization error. And I can show you this calculation maybe later.
Oh, there's another question here, Akram.
Just a quick question. So very nice talk. You showed this over-parameterization and overfitting, that it depended on essentially your norm. And there was this F infinity that thing will converge to eventually.
Yes.
And it seems that this goes basically, you have the F star function.
Mhm.
And this becomes, let's say, maybe it belongs to a certain space of functions. And the F infinity doesn't, it's a function from the F star to the F infinity. One can think of it this way.
Yes.
Which means like, basically for at least where I understand it right now, trying to find a function, in this case, it seems like you need to find, you're just finding the L2, the LUP is what tells you what F infinity is, independent of what. So in some sense, it's the model that tells you what, you already kind of know what's going to happen beforehand. Once you choose the reproducing kernel Hilbert space, you're done. Because in principle, you know for F star, what's going to happen. Of course, you may have to compute it. So how I mean, so how would you in learning? If I want to go through that, it would say like if I choose a deep neural network, then I know all I need to know is basically this mapping that goes from F star to F infinity.
Yeah.
So Yes, something is bothering me that.
Okay. Maybe I'll try to elaborate on this a little more then. So the first thing is that in this theorem, we don't have to assume F star belongs to any particular function
right.
class. If F star happened to be in the right function class, then this thing will be small.
Yes.
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 But I completely agree with you, which is like, if we're doing like a neural network, how am I supposed to know what function class the function belongs to? I absolutely agree that we won't be able to know, but this is kind of how I'm getting away with it, which is I'm only looking at a particular F star. I'm not looking at an entire function class. So I think this might be one of the differences between, say, Simon's talk and mine, where he's looking at an entire function class, looking at like the soup of F in a function class. But here, I'm just looking at a particular F star, and whatever it is, whatever function class it belongs to, then it is what it is. In that sense.
But why should I be? This is not really a criticism. I'm trying to understand. But why should I be confident
Mhm.
that I chose the right reproducing kernel Hilbert space for this particular function?
I mean, so this result doesn't require necessarily knowing that F star belongs to any particular reproducing kernel Hilbert space.
No, I
Yeah,
understand
yeah.
that.
So
So, okay,
yeah, maybe we can talk about it offline then. Yeah.
Okay.
But the alpha infinity does.
Yes, the L infinity does.
That's
Yeah.
what I'm saying.
Yeah.
Alpha infinity does. And the F star belongs to larger class.
Yeah,
perhaps.
it might. Yeah. But the thing is, I think some kind of assumption like that is necessary, because if you just do over parameterization without some weighted norm, you get some behavior like this. So I mean, I think maybe it would be interesting to look at as maybe more other algorithms besides weighted norm interpolation.
Let's maybe give an opportunity to the online folks, see if they have some questions. Well, it doesn't appear to be the case, so we can, Ryan, come and install your talk. Maybe I have one quick question then. In this case, it's a comment really. The minimum norm interpolation coming from approximation theory, and this is really related to spline theory and optimal recovery.
Yeah.
And you have a natural spline, which is a solution of this, and that motivated, I guess, the development of optimal recovery, and they even called that the spline algorithm. That was in the 70s. And I see nobody using this terminology and the fact that this is actually an optimal recovery solution for a specific model class. Am I wrong there?
No, I think you're definitely right. I mean, I think there should be more connections between our works, and I think it's related to the question I asked you offline earlier, but we can chat about it.
So we have 1.5 minutes to grab a coffee, and then Ryan will start.
The spline error